In today's video, I'm going to be doing a little down and dirty testing on TIG welding versus TIG brazing. So for the TIG welding, I'm going to be using ER70S2 filler rod. For the TIG brazing, silicon bronze as well as aluminum bronze. Also going to be doing a little aluminum bronze using alternating current on steel. All right, I'm going to make some real short runs here, 2-inch long welds, little fillets. I'm going to try to keep them all exactly the same, or at least as close as I can get them, 1/8 of an inch leg size. First up is ER70S2 welding rod. Tensile strength is 70,000 psi minimum, but oftentimes it's closer to 80. Now, if you're not interested in TIG brazing or how it compares to welding, I think this might be a pretty good little tutorial on just making a nice little weld, a nice little fillet weld on a T-joint. Keep a close arc length, like a 1/16 of an inch or less. Don't use that much torch angle. Try to keep it to about 15 degrees. And keep the hot tip of that filler rod shielded in the argon envelope, and things will go pretty well for you. Watch the front edge of that puddle. Watch it go all the way down into the root of that joint before you add rod each time. All right, let's cool that off and then put a Ford wrench on it and clamp it down to the table and see if we can break it. And even though that's 1/8 inch cold rolled steel with only an 1/8 inch leg size fillet, which doesn't wind up being a full 1/8 of an inch of metal, it's still held up. If I'd have made a smaller fillet, probably wouldn't have. But again, watching that metal go all the way down into the corner, I'm getting penetration into the root of the joint. Up next is silicon bronze, much lower tensile strength, about 50,000 psi. Still trying to keep that 1/8 of an inch leg size. Now, the technique that I use on silicon bronze or aluminum bronze is just a little forward and back, where I back up over the braze metal while I add rod. That way, if it takes me a second to add rod, if I have to fiddle around or if the rod gets stuck and I can't feed it, I'm over braze metal and I'm not over the base metal. That's the basic difference between brazing and welding, is that brazing, you're not melting the base metal. You're only melting the braze metal. We'll cool that off and then put it in the same situation. Very easy to snap. Even though I think the fillet is slightly larger than it was with the weld metal. But there's a pretty good reason for that. The silicon bronze, like I said, much weaker on tensile strength. But also, if you take a look at the difference between a weld and a braze, on the left you got a weld, you have some penetration there. And on the right you have a braze, basically a triangle. And it winds up being much less of a throat, much less of a cross-sectional area, and it just doesn't lend itself well toward a single-sided joint like that. It needs to be welded on both sides for it to have a lot of strength. Up next, we're going to do a little aluminum bronze. This is the A2 version of aluminum bronze. It's got a very high tensile strength, pretty much the same as the ER70. So let's see how it does. Same exact technique. A lot of times aluminum bronze is sluggish. You really have to clean that filler wire because it does have quite a bit of aluminum, 9 to 11%. This version anyway, and it can wind up giving you some aluminum oxides in the puddle. But I Scotch-Brited it before doing this joint, and it came out pretty shiny. Cool it all the way down. Same thing. It's noticeably harder, that I notice, even with the Ford wrench in my hand, but you can't probably tell it on the video. Notice it'll be more difficult to snap, but still snaps relatively easily. Not impressive at all. Now let's go to aluminum bronze using alternating current, AC. Now the thing about this is you can use any machine basically, but if you have an inverter, you can set the AC balance for a very high percentage of electrode negative or very little cleaning. And it's almost like welding on DC. You can pinpoint the heat a lot. I use this method along with a preheat for a lot of general cast iron repairs. Not everyone, but you can see how that cleaning action, the etching area, just kind of cleans the path for the brazed metal to flow, just same as it does on aluminum. It also keeps the filler metal really clean. The filler metal does have aluminum in it, keeping it from scumming up. And I just had a lot of success using this method, alternating current, same settings I would do on aluminum almost. And this is much more difficult to break here. It's still going to break, but it's bending the base metal not deforming it, but it's taking a lot more effort to snap it. Again, still not impressive though as far as just being able to hold up compared to a weld. And let's take a quick look at that too. If you look at a brazed fillet here with no penetration, no depth of penetration, it's going to look something like this, like a triangle. 1/8 of an inch leg size equals only about 0.88 throat size, and that's just not that much metal to hold back. If we take a look at some 055, some 1.4 millimeter 308 stainless sheet metal here, and we set up the same type joint with a very large fillet. I'm using large filler metal with a leg size roughly 5 times the thickness of the sheet metal. I put that in the same clamping arrangement here. It has no trouble, even on a one-sided joint there, it has no trouble holding back and bending and not failing. Or even on that 1/8 inch thick, if I take one of those pieces and put extra metal, I weld it both sides and then put a big ugly fillet on one side, large leg size, that'll hold because it's done on both sides. So you have to compensate for the lack of strength and the lack of penetration of brazed metal. It needs to compensate with a much larger fillet if you want a decent strength joint. What you're looking at here is a oxy-fuel brazed, fillet brazed joint. Mike Zanconato is a bike builder. I was talking to him on Skype the other night. We had him as a guest on the podcast, and that'll air pretty soon. That's the Welding Tips and Tricks podcast. You can find it on iTunes or Stitcher, several other places. Well, we got to talking about fillet brazing. This is one method of building bikes that he's experimented with. But again, this is torch braze, but you see the rather large fillets. This is very thin wall tubing, and there's probably some fillet on the inside too because flux was used along with the oxy-fuel torch. Well, that got me to thinking, what if we just packed a lot of silicon bronze rod on a bicycle type coped joint? And this is some tubing that Mike sent me years ago, and I did a little video on welding it. So today I'm going to use silicon bronze on this stuff and see if we can destroy that braze joint. Try to get as good a fit up as possible, and then we get a tack on there, and then I'm just going to really make a big brazed joint. I'm going to use a much bigger filler than I would normally use. I'm going to use a 3/32, 2.4 millimeter diameter silicon bronze filler rod, and I'm just really kind of loading it up, going a little bit overboard so that I make sure to have a lot thicker brazed metal than what the base metal is. And you're only going to get so much thickness here on the sides, but on the sort of the crotch of that weld, I'm really loading that up on both sides. Now I'm probably going a little bit overboard on the amount of filler I'm putting in here, especially right here. But right here you can see just how liquid and fluid this stuff gets. If you overheat it, it can actually kind of run out on you. And I'm kind of like on the ragged edge there of getting it a little too hot. And like you can see, I think I went overboard a little bit with the amount of filler I put in there. But again, I wanted to see if it's going to hold. Now, this is a malleable iron pipe fitting here, threaded fitting. And I'm just going to weld it to that base plate just to use it to help me test. And a while back I did these piggy banks for last Christmas for gifts for my kids. And I welded some of these pipe fittings, these malleable iron pipe fittings on there, very similar to cast iron. So I want to see what kind of a job silicon bronze is going to do holding that on this piece of steel. I want to use it as an anchor point to test the bicycle. So I'm kind of testing everything at one time. Now I weigh in this video here, I'm about 205 to 210 pounds. And I completely picked my weight up in that direction with no problem. I'm going to try to do the same thing here. And so a large fillet looks like doing the trick. Silicon bronze is a great rod to have in your arsenal. It's really good for wear resistance. You can build up a little chafed area on a piece of hydraulic tubing or something like that, and it's very wear resistant. And you can weld on really thin metal because you don't have to actually melt the base metal. You can weld stainless to carbon to cast iron to copper to brass, any of those things. You can join them with silicon bronze. It's not that strong as you saw in the video.
It's great for prototypes also because it doesn't warp much, it doesn't move much, and you can grind it off really easily and pull something loose and reposition it if you're experimenting building something. But if you're doing anything structural, again, you saw how easy it just snapped on a one-sided fillet. There are concerns there. So on the other side of the coin, when I put a very large brazed joint, a very large fillet, and packed a lot of rod on that thin wall tubing, it seemed to hold up better than the tubing did. So it's got a lot of uses. You just don't want to indiscriminately use it for structural stuff. Aluminum bronze, again, a little bit stronger, but typically doesn't flow as good unless you got really good gas shielding. If you use AC though, that tends to clean it up just like it works on aluminum. That cleaning action cleans it a little bit ahead and makes it flow and wet in there, which is why I like to use it on some cast iron repairs. We'll get into some of that later on. For now, that's it. We'll see you next time.